Alrighty. Good morning, lads and ladies. Welcome back to Calc 1 Honors. Today, we are going to dive a little bit deeper into this connection between increasing, decreasing, and the derivative of a function. In particular, we're going to look at section 4.3 in the textbook. But before I get into anything super specific, I wanted to share something with you that I decided to share with my Calc 2 students because I'm at a place with them now where I'm trying to get them to think about improper integrals, which are these objects that measure area of regions that are very, very long, maybe infinitely long. One of the sort of surprising things that happens there, sometimes you can make a substitution that takes that region and like maps it into another region with the same area, but is not infinitely long. And the fact that you can do that on its own is kind of surprising. I reference them to the section that we are going to cover at the end of the semester called 5.5, a U substitution. But there's kind of a little bit of prerequisite knowledge that I wish they had had. And I realized the right way to do that is to introduce it to you guys back here in Calc 1 so that you've seen this concept before you have to apply it in some really difficult way. And I was searching around trying to find the right place to share or describe this for them. And I found something really neat on 3 Blue 1 Brown, which is a channel you may have heard of on YouTube. So before we get into the meat of today's lecture, I just wanted to share something with you from the old internet. This video, so 3 Blue 1 Brown has lots of wonderful mathematics videos. If you're a math nerd and you haven't been looking at 3 Blue 1 Brown, you've been doing YouTube wrong. It's awesome. This guy's name is Grant, and he has videos about all sorts of really cool things. The stuff that I think might be especially interesting to you guys is this playlist on the essence of calculus. So where's that? Yeah, here's I was watching a little bit of it. So if this is the right link, and I think it is, asking an awful lot of my internet connection right now. There we go. Yeah, you might want to check this out. He presents a really good high-level kind of general, not at all nitty-gritty, but very, very good intuitive way of thinking about all of the things that we're going to do in this class. And that's wonderful. So I'm going to go ahead and paste this for you here. Come on. I know that most of you guys have some experience with calculus outside of this class, regardless of whether you do or not. I think you will get something out of this Essence of Calculus video series. It's a lot of fun. I watched it years ago. I think it's just a few years old now. But as these were coming out, I was watching 3 Blue 1 Brown's other stuff, and it's all wonderful. I encourage you to take a look at that. The real thing, though, that I wanted to share with you guys, kind of looking down the line, is this, which is a, is this it? I think, yeah. So I'm gonna go ahead and actually play the first few seconds of this video because he talks a little bit about how you can think of functions as transformations rather than as graphs. Graphs are great if you're studying functions whose input and output are both one-dimensional. Right, so like the number line is a one-dimensional thing. The functions we've studied so far take in numbers and spit out numbers. That's why we're able to look at their graphs. Their graphs are 2D because they have 1D input and 1D output. But most of the graphs that mathematicians would like to study are not so simple. You know, if you're studying complex functions, then your inputs and outputs are both two-dimensional, which means your graph overall would be four-dimensional, which is pretty hard to draw. So thinking of functions as transformations turns out to be the right way to think about functions for a lot of slightly more advanced concepts. And I'll let Grant say it here. I'm not going to play the whole video, just the first few minutes. But
picture yourself as an early calculus student about to begin your first course. The months ahead of you hold within them a lot of hard work, some neat examples, some not so neat examples, beautiful connections to physics, not so beautiful piles of formulas to memorize, plenty of moments of getting stuck and banging your head into a wall, a few nice aha moments sprinkled in as well, and some genuinely lovely graphical intuition to help guide you through it all. But if the course ahead of you is anything like my first introduction to calculus, or any of the first courses that I've seen in the years since, there's one topic that you will not see, but which I believe stands to greatly accelerate your learning. You see, almost all of the visual intuitions from that first year are based on graphs. The derivative is the slope of a graph, the integral is a certain area under that graph. But as you generalize calculus beyond functions whose inputs and outputs are simply numbers, it's not always possible to graph the function that you're analyzing. There's all sorts of different ways that you'd be visualizing these things. So if all your intuitions for the fundamental ideas, like derivatives, are rooted too rigidly in graphs, it can make for a very tall and largely unnecessary conceptual hurdle between you and the more quote-unquote advanced topics like multivariable calculus and complex analysis, differential geometry. Now, what I want to share with you is a way to think about derivatives, which I'll refer to as the transformational view, that generalizes more seamlessly into some of those more general contexts where calculus comes up. And then we'll use this alternate view to analyze a certain fun puzzle about repeated fractions. But first off, I just want to make sure that we're all on the same page about what the standard visual is. If you were to graph a function, which simply takes real numbers as inputs and outputs, one of the first things you learn in a calculus course is that the derivative gives you the slope of this graph, where what we mean by that is that the derivative of the function is a new function, which for every input x returns that slope. Now, I'd encourage you not to think of this derivative as slope idea as being the definition of a derivative. Instead, think of it as being more fundamentally about how sensitive the function is to tiny little nudges around the input. And the slope is just one way to think about that sensitivity relevant only to this particular way of viewing functions. I have not just another video, but a full series on this topic if it's something you want to learn more about. Now, the basic idea behind the alternate visual for the derivative is to think of this function as mapping all of the input points on the number line to their corresponding outputs on a different number line. In this context, what the derivative gives you is a measure of how much the input space gets stretched or squished in various regions. That is, if you were to zoom in around a specific input and take a look at some evenly spaced points around it, the derivative of the function of that input is going to tell you how spread out or contracted those points become after the mapping. Here, a specific example helps. Take the function x squared. It maps 1 to 1 and 2 to 4, 3 to 9, and so on. And you could also see how it acts on all of the points in between. And if you were to zoom in on a little cluster of points around the input 1, and then see where they land around the relevant output, which for this function also happens to be 1, you'd notice that they tend to get stretched out. In fact, it roughly looks like stretching out by a factor of 2. And the closer you zoom in, the more this local behavior looks just like multiplying by a factor of 2. This is what it means for the derivative of x squared at the input x equals 1 to be 2. It's what that fact looks like in the context of transformations. If you looked at a neighborhood of points around the input 3, they would get roughly stretched out by a factor of 6. This is what it means for the derivative of this function at the input 3 to equal 6. Around the input 1/4, a small region actually tends to get contracted, specifically by a factor of 1/2. And that's what it looks like for a derivative to be smaller than 1. Now, the input 0 is interesting. Zooming in by a factor of 10, it doesn't...
So I'm going to stop here. But I hope that that's enough to kind of get you interested. Thinking about functions this way as inputs getting mapped to outputs is how we teach what functions are at first, and then we shift to this thing where we're talking about graphs. Sometimes coming back to the input-output thing, specifically if you have some idea of what the input and output spaces look like geometrically, can be a much more powerful way of doing it. So thinking of functions and derivatives as transformations is in this video. And it's this second concept here that is going to be really helpful when we get to section 5.5 and we start talking about use substitution. because we'll be doing coordinate transforms, which are exactly this. They are transformations. And the thing called the differential that we just learned about that we'll need to calculate for those substitutions will be explaining how much the input space gets stretched or squished. And then this is a very big deal in Calc 2 when we talk about sometimes squishing an infinitely wide input space down to a finitely wide input space. And that can be a pretty crazy thing. So I think having seen this picture before is going to be really helpful. But it's not directly connected to the rest of what we're doing today. So I'm going to come back over here and get started with class proper. All right. Oh, the other kind of intro thing I wanted to talk about is exam 2. Now, I would like us to have exam 2 before spring break. That would mean exam 2 would be next Friday. I'm not 100% sure if that's viable without moving section 4.7 to exam 3. So let me start writing these things down. Today's the 24th, right? Yeah. Okay. So today, my book just ripped the nastiest ass. All right, today we're going to talk about section 4.3 on derivatives and graphs. But then I also want to make a little note here. Next time on Friday, I will let you guys vote on 2 options, 2 paths for exam 2. The first path here is that we delay the test until after spring break. And test ends, test material cuts off at section 4.7, which is the normal place. That section is on applied optimization. The other path here is that we have exam 2 next Friday before spring break. But the exam material would have to cut off a little bit sooner, which would mean I'd have to push section 4.7 onto exam 3. So if you look at the syllabus here, you'll see the normal timeline. Ideally, we would be able to finish applied optimization before spring break and then have the test in time to include section 4.7. This is a little bit difficult. It's not totally impossible, but it's a little bit difficult given that the section we're talking about today is going to take the full day. This curve sketching section is likely to take a full day. It's a little bit challenging. And then the applied optimization stuff is going to take a full day as well. It's all really tough. So this would mean we wouldn't really finish the exam material until Wednesday, and I would test you on that stuff on Friday. That's not at all fair. So the other option here is to take section 4.7 and push this after break. So we'd have the exam next Friday before break, but have the exam 2 material cut off at section 4.5, which is what we're going to do this. Let's see, that would be on Monday. So I will leave it up to you guys what you want to do. There are good reasons to do both. So before I turn you loose to think about these things on your own, let me try to influence you a little bit in both directions. Having the exam before break is really nice because people forget shit over break. You know, I'm not 100% ignorant of what students like to do on spring break, even though, you know, it's Rona time. I'm sure plenty of people will be doing things other than study math over spring break. So if you give yourself a whole week of not doing mathematics, that has a way of really destroying test scores because we forget things if we don't practice them and practice them often. On the other hand, if we were to split up the exam material and have the test before the break, that means taking something that very naturally belongs on exam 2, which is section 4.7. It's applied optimization, has to do only with derivatives, very much belongs with the stuff that we've talked about recently, and putting that on exam 3. So it would make studying for exam 3 a little bit harder in a couple of ways. First, it would mean exam 3 has more shit on it, but also this shit that would be pushed onto exam 3, if we were to delay the test, would not really belong with the other exam 3 stuff. So most of exam 3 stuff is integrals and areas. 4.7 would kind of be the only thing there that is still connected to applications of the derivative. So these are our two choices. We can either put the test off until after break and have all the normal material on exam 2 running up through 4.7. This keeps the material together, but gives you, you know, a week of like time to forget between when you learn the material and when you're tested on it. So pros and cons. The other option here is to have the exam next Friday before break, but lose some of the material that's normally on test 2 and put that on test 3 instead. So here, you know, you don't have the time to forget, right? It's before break. It's before we lose all those brain cells to tequila and whatever else. But it means that you're going to have to kind of recall some differentiation material when it comes time for exam 3. No need to make a decision right now. I'm just letting you know that this is a decision I will be letting you guys make next time we meet. Okay, so that's enough of that. Let's get into section 4.3, which is in the syllabus titled like graphs of f and f prime. Really the section title is how derivatives affect the shape of a graph. All right. The place this all begins, we have seen that if f of x is decreasing, then f primed of x will be negative. And if f of x is increasing, then f primed of x will be positive. And this comes from the kind of standard picture, thinking about f and its tangent lines. You know, if I have a decreasing function, and I take a few sample points wherever, look at the slopes of the tangent lines, these will all be negative, right? So this is the graph of f of x. And you know, f primed is the slope of these tangent lines. Will be negative. On the other hand, if I have an increasing function, and I take some sample points, think about the tangent lines at these points. These will have positive slope. Right, that's the basic idea. So you know, if f is decreasing, then f primed is negative, and if f is increasing, then f primed is positive. Turns out the converse is true, at least as true as it can be. So let me go ahead and state the converse. It says, you know, if you're decreasing, then f primed is negative, or if you're increasing, then f primed is positive. The converse to that statement is if f primed is negative, then f is decreasing. And if f primed is positive, then f is increasing. And this is as true as it can be. So let me go ahead and give the statement here. This theorem. If f of x is differentiable and increasing on an open interval I, then f primed of x is positive for all x's in I. Also, if f of x is differentiable and decreasing on an open interval I, then f primed of x will be negative for all x in the interval I. Right, so this is a true statement, and we need these hypotheses, like f has to be differentiable. And it really only makes sense to talk about increasing and decreasing on open intervals. But this is good. What this tells us is that if you want to know where f is increasing, you can figure out where f prime is positive. And if you want to know where f is decreasing, you can figure out where f prime is negative, as long as the function in question is differentiable, at least differentiable at all of the places you're looking. We don't like to mess around too much with functions that aren't differentiable. Pretty much all the functions we play around with are differentiable almost everywhere. Maybe the exception of 1 or 2 points in their domain. So this isn't a harmful thing for us. We can do this and be quite happy about it. So let's grab an example or two. Let's see if we can find where this guy is increasing and decreasing. 3x to the 4 minus 4x cubed, e.g. Example. Find where f of x equal 3x to the 4 minus 4x cubed minus 12x squared plus 5 is increasing and decreasing. Okay. This function is a polynomial, so it is differentiable everywhere. Its domain is all real numbers. So what we're going to do is we're going to differentiate this bad boy and try to figure out where f primed is positive and where f primed is negative. All right. So let's calculate f primed. f primed here is going to be 12x cubed minus 12x squared. That's this guy's derivative minus this guy minus 24x. So if I want to find where this function is increasing and decreasing, it suffices to find where f primed is positive and negative. Here's f primed. How do I figure out where f primed is positive and negative? I need to solve the inequalities f primed of x is greater than 0 and f primed of x is less than 0. Turns out we can solve both of these at the same time. Now, I'm not sure how strong you guys' inequality skills are, but I do have some things in the modules for you to look at. So here we are in the right place, modules. If you look at this page, Paul's online notes solving inequalities in the review material module, or here's the other ones. Here's this one, solving rational inequalities, solving polynomial inequalities. These are all really good, right? So they give us some examples of inequalities and shows us how to solve them. If you don't remember how to do this number line thing with test points, you need to remember. So I will be walking you guys through it with a couple of examples today. But it's important that we learn how to solve inequalities like this. The idea is we're going to find the critical numbers. We're going to find the places where f prime is equal to 0 or undefined, plot them on a number line, and then test a point from each region that creates. There are some shortcuts for this stuff, and I will show you some of those shortcuts. But you need to be comfy with the basics. So here we go. If I'm going to figure out where this function is positive and negative, that means I need to know where it's equal to 0, because where it's equal to 0 is where it's capable of changing from being positive to negative or negative to positive. So I'm going to factor this. Right, I see it right away. I can factor out a 12x, and then what's left is going to be x squared minus x minus 2. And the remaining pieces here can be factored as x minus 2 times x plus 1. So here's the factored form of f prime. So my critical numbers places where f prime is equal to 0, f prime is never undefined, f prime of x equals 0 at x equals -1, 0, and 2. And f prime of x is undefined nowhere, right? Because f prime here is a polynomial. But if it were a more complicated function, we would also want to keep track of anywhere it's undefined. So these are my critical numbers. I'm going to plot them on a number line. So -1, 0, 2. The spacing doesn't matter, just the relative placement. So like -1 is the leftmost thing, 0 in the middle, and 2 on the right. That's all that matters. And then from each of these regions, I will test a point. So over here, like to the left of -1, I could test x equals -2. That is an x value that is in this region. F primed of -2 is 12 times -2 times -2 minus 2, that's -4, times -2 plus 1, that's -1. So this is negative, this is negative, and this is negative. And if you multiply 3 negative things, you get a negative thing. So f primed of -2 is less than 0, it's negative. We're going to do the same thing between -1 and 0, between 0 and 2, and to the right of 2. Between -1 and 0, I could test x equals -1/2. I need something that's between these. I can't use either boundary. It has to be actually between them. So imagine plugging in -1/2. I'm not going to do it like I did here. I'm not going to do it explicitly because I don't care what the number is. I just care whether it's positive or negative. So if I plug in -1/2, this piece would be negative, right? It would be -6. This piece would be negative. -1/2 minus 2. It's -2.5, whatever. It's negative. And this piece would be positive. So I would have a negative times a negative times a positive. So f primed of -1/2 is positive. Between 0 and 2, I could test x equals 1. F primed of 1 is 12 times 1, which is positive. 1 minus 2, that's negative. And then 1 plus 1, that's positive. So it'd be positive times positive, which is negative. F primed of 1 is negative. And then to the right of 2, I could test something like x equals 3. F primed of 3, well, this would be positive. 3 minus 2 is 1, that's positive. 3 plus 1, that's 4, that's positive. So positive, positive, positive. This is definitely positive. F primed of 3 is definitely positive. And this is my number line for f primed. So f primed is negative. For x's in the set -infinity up to -1, unioned with 0 to 2. And this means that f of x is decreasing on the interval -infinity to -1, and 0 to 2. And same sort of thing, f primed of x is greater than 0 for x in the set -1 to 0, unioned with 2 to infinity. And this tells me that f of x is increasing on precisely those intervals from -1 to 0 and from 2 to infinity. Sorry, 1 second. Malachite, what on earth are you doing? I cannot deal with it right now. All right. So this is how we find where a function is increasing and decreasing. All right, we need to solve the corresponding inequalities for f primed. And the way we do that is by making this number line. It's correct that brackets would indicate a closed interval. And we wouldn't want to say that a function is, so let me graph this function for you. Let me take a look and kind of talk a little bit about why we use open intervals. It's a good question. All right, here we are. So this is that function. And you'll notice that from -infinity up to -1, we are decreasing. And from 0 all the way over here to 2, we are decreasing. Now, at -1, we are neither increasing nor decreasing, right? Let's look at these. I wouldn't want to use a closed bracket here on the -1 because I wouldn't want to say we are actually decreasing there because we're not, right? I'm not decreasing at this point anymore. I'm decreasing everywhere over here, but at this point, I am turning around. I am in the process of turning around. It is not fair to say that I'm decreasing here. If you could argue that you're decreasing there, you could also argue that you're increasing there. So briefly, instantaneously, just for 1 second there at x equals -1, we are neither decreasing nor increasing. We are in transition between one and the other. The same thing is true at 0, right? Here's the point at x equals 0. I'm increasing over here and I'm decreasing over here. So it doesn't make sense to say I'm increasing at x equals 0, nor does it make sense to say I'm decreasing. That's why we use these open intervals, right? So this is something that is supposed to be talked about in pre-calculus, but I don't think they hammer on it quite enough. When we talk about intervals on which we are increasing or decreasing, we always use open intervals because at the points where we change from one to the other, it doesn't make sense to say that we're doing either. As I run over the top of a hill, right? Think about it, you're running up the hill, you're running up the hill, you're running up the hill. As at that moment when you crest the top of the hill, you're not going up anymore. You're also not going down yet. You are in transition. And that's why we always use open intervals for these. Any questions on this problem? All right. You may notice a pattern here, right? We're blinking back and forth, negative, positive, negative, positive. It's not always going to be like that, but there is a neat connection between the multiplicity of the factors here and the sign changes at the corresponding critical numbers. The fact that the multiplicity of x plus 1 here, you guys remember what multiplicity means? It's the power of the factor, right? So this is like x plus 1 all raised to the power of 1. The multiplicity is what dictates whether you change sign or not. So the x equals -1 here is coming from the x plus 1 factor here. This x plus 1 factor is of multiplicity 1. That's the power of the factor. Since that is an odd multiplicity, I knew ahead of time that this was going to change sign. And the same is true for the others. The 0 factors, the 0 on the number line is coming from this factor. This is x minus 0 to the first. The power here is 1. So I could have told you a priori that you would change sign there. You can save yourself a lot of time by learning this multiplicity trick. And this multiplicity trick is described in one of those links in the modules. So you can please read about that there. You'll save a lot of time doing this. All right. I do want to talk a little bit more about this example. Specifically, I want to talk about what's going on at these critical numbers and how we could know that just from the number line. So let's focus our attention on this guy, 0, 5. Specifically, it's just x equals 0, right? Don't worry about the y value. Just at x equals 0, what's happening? X equals 0 is right here on my number line. And according to my number line work, we are increasing to the left of 0 and decreasing to the right of 0. So I'm going to superimpose another page on top of this and try to answer a slightly separate question. Or maybe I'll just redraw it. Yeah. All right. So, I'll just redraw. So what's going on? Just redraw number line for f prime. We had -1, 0, and 2. Okay, and f prime was negative here, positive here, negative here, positive here. This means that f is decreasing here, going downhill. This means that f is increasing here, we're going uphill. This means that f is decreasing here, we're going downhill again. And this means that f is increasing here, going uphill again. Look at just what I have here. At 0, for example, we said we wanted to pay attention to what's going on at 0. I go from increasing to decreasing, which means I'm going uphill, 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 then downhill, downhill, downhill. What does that tell us about what's happening at 0? Or what do you notice? What kind of feature to the graph exists right here at x equals 0? What would you call this point? Think about what we were talking about on Monday.
The local maximum.
Yeah, it's a local max. And if you think about it, since we go from increasing to decreasing there, the only way for that to happen is if we roll over the top of a hill. That must be what's going on. As you go from increasing to decreasing, you have to go over a little hill, which means that has to be a local max. So what about over here at -1? Where we go from decreasing to increasing.
Yeah, local minimum.
Yeah, this has to be the bottom of a little valley. This has to be a local min. And then similarly over here, we go from decreasing to increasing again. That means we had to roll through the bottom of a little valley. This must be another local min. And if you compare this to our graph, you'll see indeed we have a local min, then a local max, then another local min. So this is called the first derivative test. For local extrema. And I'll state it as a theorem. Let f of x be a continuous function, or be a function, I should say function continuous at the critical number x equals c. If f primed of x goes from negative to positive at x equals c, then the original function f of x must have a local min at x equals c. Right, that's f prime going from negative to positive, means f goes from decreasing to increasing, means you had to roll through the bottom of a valley, which means that point is a local min. And then you also have the statement if f primed goes from positive to negative at x equals c, then f of x itself must have a local max at x equals c. And that's similarly logical, right? If f prime goes from positive to negative at some critical number, then you're increasing to the left and decreasing to the right, which means you're going uphill then downhill, which means you rolled over the top of a little hill, which means the center of that hill is a local max. This is the first derivative test, and it's the most useful way to find mins and maxes. This is anytime we want to find mins and maxes, this is how we do it. We make the number line like this. We find where f is increasing and decreasing, and that will tell us also where we have local mins and local maxes. It's not the only way to do this. There's also something called the second derivative test. And in certain cases, that can be a little bit faster. But usually, if we're doing one thing, finding mins and maxes, we're also trying to do the other thing, find where f is increasing and decreasing. Usually, we do those together. So that means we're essentially always using the first derivative test. But I will show you another trick down the road. Before we do that, though, I need to talk to you a little bit about how the second derivative affects the shape of the graph. So are there any questions on what we've done or said here?
Can you go back to like the previous page?
Sure. Yeah, this is where we cooked up that number line.
Okay, thank you.
Of course. So, let's see, I think there's one or two other things I want to mention before we go. So increasing, decreasing terms. Yeah, the book has their own way of like laying out that number line stuff. They make a table with each of the factors and then say whether the factors are positive or negative. I think this is a little bit clumsy. This is not how most people do this. So I would look at the Paul's Online Math Notes for solving those inequalities. That's really what we're doing. And here you see the first derivative test illustrated, right? Increasing, decreasing, f prime positive, f prime negative, that means we have a local max. Decreasing to increasing, f prime negative to positive, that means we have a local min. And then here's some ways this can fail. If f prime, it may be c as a critical number, but f prime is positive on both sides, or f prime is negative on both sides. Well, that means that you don't have anything. Let's do example 3. Let's find the local mins and maxes for that function. X plus 2 sine x. All right, and they asked us to just pay attention to the interval 0 to 2 pi. That's fine, we can do that. We should begin by taking our derivative. We need to find g prime and then build a number line for g prime. That will tell us where g is increasing and decreasing. And so we'll be able to say whether our critical numbers are local mins, local maxes, or neither. All right. Sorry, I had to pick my nose there for a second for you guys. Probably didn't want to see that. G prime, if I take the derivative here, the derivative of x is 1 plus the derivative of 2 sine x is 2 cos x. So if I want to find my critical numbers, that means we need to find where g prime of x is equal to 0 or g prime of x is undefined. We're lucky here. G prime, this thing again, is never undefined. This never happens. But this can certainly happen. So that would mean 1 plus 2 cos x is equal to 0, which means 2 cos x is equal to -1, which means cos x is equal to -1/2. And that is a trigonometric equation that has infinitely many solutions. But I was told to just pay attention to the interval 0 to 2 pi. I'm not interested in anything but the solutions in this interval. So where between 0 and 2 pi is the cosine of x equal to -1/2? This might have been something that was on our interview quiz for some of you. So here's my unit circle. Cosine being -1/2 corresponds to the x value on the unit circle being -1/2. So I'm looking at these 2 points here, which correspond to these angles. So this guy up here, this point is -1/2 comma √3/2. And he occurs at the angle 2 pi over 3. What is this guy down here? What is this angle?
Is that by
Yeah, very good. 4 pi over 3. All right. So those are my critical numbers. So now I need to make a number line for G prime. And on that number line, I'll go ahead and mark this side over here as 0 and this side over here as 2 pi, because again, I don't care about what happens outside that interval. I'll put 2 pi over 3 here, and I'll put 4 pi over 3 here. The spacing doesn't matter, just the order. Between 0 and 2 pi over 3, I could test pi over 2. G primed of pi over 2 is what? It's 1 plus 2 times the cosine of pi over 2. Well, what is the cosine of pi over 2?
that would be 0?
0, good, yeah. So G primed of pi over 2 is 1. In particular, it's positive. Between 2 pi over 3 and 4 pi over 3, what would be a good test point? Yeah, good, pi. We could test x equals pi here. So what is G primed of pi? Well, it's 1 plus 2 times the cosine of pi. What's the cos of pi?
-1.
Good, yeah, thank you, Julio, -1. So G primed of pi is 1 plus 2 times -1. 2 times -1 is -2. 1 plus -2 is -1. So this is -1, which is less than 0. So G primed is negative between 2 pi over 3 and 4 pi over 3. And to the right of 4 pi over 3, I could test 3 pi over 2. G primed evaluated at 3 pi over 2 is 1 plus 2 times the cosine of 3 pi over 2. What is the cosine of 3 pi over 2?
Power to 0.
So 3 pi over 2, that's the south pole of the unit circle down here, right? What is the cosine here?
Should
You
be-
might have said it correctly, Julio. I just couldn't hear you. I'm sorry.
Yeah, it should be 0, right?
Yeah, 0. Very good. So the cosine of 3 pi over 2 is 0. So G prime of 3 pi over 2, this is positive 1 again, which is positive. So here we are. So I know that G is increasing from 0 to 2 pi over 3, decreasing from 2 pi over 3 to 4 pi over 3, and increasing from 4 pi over 3 to 2 pi. Specifically, what must be going on right here? And what must be going on right here?
Like a local maximum and then a local minimum.
Yeah, G has to be increasing here, decreasing here, and increasing here. So here we roll over a local max. And here we roll through a local min. And that's the game. So we have a local max at 2 pi over 3, and we have a local min at 4 pi over 3. So I'd say g of x has a local max at x equals 2 pi over 3. And the max value is g of 2 pi over 3. G of 2 pi over 3, that's 2 pi over 3 plus 2 times the sine of 2 pi over 3. So that's 2 pi over 3 plus 2 times what? What is the sine of 2 pi over 3? Does anybody know that? What is this piece?
Square root 3 over 2.
Good, root 3 over 2. So we need to know our unit circle. The 2's here can cancel, and you get 2 pi over 3 plus the square root of 3. So we have a local max. Where is the local max? It's at 2 pi over 3. What is the local max? It's 2 pi over 3 plus root 3. Also, we can say g of x has a local min at x equals 4 pi over 3. And the min value is g of 4 pi over 3, which would be 4 pi over 3 plus 2 times the sine of 4 pi over 3, which is 4 pi over 3 minus the square root of 3. Because the sine of 4 pi over 3 is negative root 3 over 2. So this is all the local extrema from that interval. Can we comfy with what happened here, how we found these guys? And what we're saying down here, the language? Okay. And here we go. Here is the picture that comes along with this, right? Here's our local max, here's our local min. And they gave the same values, right? Okay. So this is how we find mins and maxes using the first derivative. Not a big deal, not super hard, but is important, right? Not a big deal in the sense that it's not super challenging, but it is a big deal in that finding these extremas is hugely important. This is one of those things that's kind of promised to you, or kind of teased to you all through your algebra and pre-calculus classes, where they give you the graph and say, here's the min, here's the max, whatever, find these. But you could never find those x values yourself unless you had like a parabola. Those were easy because you just had to find the vertex. But anything else, you were like shit out of luck. Now you can do it. Now you can do it. If you want to find local mins or local maxes purely by hand, no graphing, just with the algebra and the calculus, it can be done. Take the derivative, find the critical numbers. That means setting the derivative equal to 0 and also finding where the derivative is undefined. Build a number line, and then apply the first derivative test. Where you're increasing to decreasing, it's got to be a max. Where you're decreasing to increasing, it's got to be a min. Okay. So that's what we can do with the first derivative. What about the second derivative? Does he tell us anything? So here's the idea. This is called curvature or concavity. And to kind of introduce you to this concept, I'm going to just draw a picture. It's going to be a graph of f of x. And then I'm going to use the kind of tools that you guys had to apply on exam 1 to estimate and sketch the graph of f prime. Let's do it. Okay, here's the graph y equals f of x. And I'm just going to take a few points along this graph where I will estimate the derivative. We'll call this 1, call this 2, call this 3. I know this is way out here. I'll call this 4. Right. If I look at the graph of f here, the tangent line looks something like this. So I would estimate that f primed of 1, it's clearly negative, and it's pretty friggin' steep. Let's say that's like, negative 3. All right, maybe it's steeper, I don't know, but here it's definitely less steep. To estimate f primed of 2 to be maybe like negative 1, something like that. Here it's less steep still. I'd say that this guy, f primed of 3, is like negative 1/2 maybe. And over here it's still less steep, still negative, but less steep. So f primed of 4, I don't know, maybe like negative 1/4. Something like this, yeah? So if I wanted to use this to sketch the graph of f primed, we can. Let's see, f primed is all negative, so I should draw my picture a little more like this. First, here's the x-axis. This will be the graph y equals f primed of x, estimated in the same way that you did on the test. So here's 1, 2, 3, 4. I said f primed of 1 looks to be about negative 3. So, okay, down here, negative 3. So the point 1 comma negative 3 would be on the graph of f primed. F primed of 2, I said that looks to be about negative 1. So 0.2 comma -1 would be on the graph of f prime. F prime of 3 we said is like -1/2. So that's something like this. And f prime of 4 is like -1/4. That would be something like this. So here's what the graph of f prime looks like. Yeah, something like this. So thinking about the stuff that we've been doing today, talking about, increasing, decreasing, blah, 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 what would you say about f primed here?
It doesn't have any like local maximums or minimums.
I'm sorry, can you say that just a little bit louder?
Like it doesn't have any local maximums or minimums from what we can see.
That's true. F, as I've drawn it here, doesn't have any mins or maxes, and f prime doesn't have any roots, right? Doesn't have any x-intercepts. F prime is never 0, never changes sign. What else do we notice about the function f primed here? Is it increasing or decreasing? Increasing, yeah. F primed is increasing. So what would that tell me about f double primed? So that means the derivative of f primed of x, which is f double primed of x, must be, if f primed is increasing, then what must be true of its derivative? The derivative of an increasing function is
Also increasing.
not necessarily increasing. Actually, f double primed as drawn here would itself be decreasing. But more important, it's positive. Right? The derivative of an increasing function is positive. So if I look at this picture, so I'm going to take this and come back up here and make some collective comments here. This function, f of x, has f primed of x less than 0 and f double primed of x greater than 0. The fact that f primed is less than 0 tells us that the original function is decreasing. And it is, right? The original function here is decreasing. The fact that f double primed is positive tells us that this is what's called a concave up function. So we're talking about curvature or concavity. And the idea is that by kind of estimating f primed and drawing the graph of f primed, we can say something about f double primed. Any function whose graph is shaped like this has to have a positive second derivative. And the graph shape that we correspond with that is called concave up. So what I'm going to do for you now is draw some graphs and classify them according to their shape and whether the first and second derivative are positive or negative. If you want to, here's what f double prime's graph would look like here. F double prime's graph is actually going to look a lot like the original graph f of x. The tangent line here, is positive. So I'd say f prime primed of 1, it's like 2. Tangent line here is positive, but less steep. So f prime primed of 2 would be like 1. Positive, but less steep. F prime primed of 3 would be like 1/2. So the second derivative, 1, 2, 3, is going to look like 2, 1. It's going to look something like this. In particular, it's positive. Right. So f double primed here is positive. So let me zoom out for a minute. It's really the top two things here that matter. The sketch of f double prime is not super important here. But the main idea is that from this graph, we're able to deduce two things. That f prime's graph looks like this. Specifically, f prime is everywhere negative. But that f primed is itself increasing, which means f double prime has to be positive. So f prime is negative because we're decreasing, and f double prime is positive, which tells us that we are concave up. All right, here comes the good stuff. We have to take all the possible permutations of signs for the first and second derivative. Graph shapes according to the signs of f primed and f double primed. If f primed is positive and f double primed is positive, this means we are increasing and concave up. What this looks like is we're increasing and our rate of change is also increasing. So we're always going uphill, but we're going uphill faster and faster and faster. This is kind of like having your velocity and acceleration both being positive, right? Velocity and acceleration both being positive. It's possible also that f primed is positive, but f double primed is negative. This would mean we are increasing, but concave down. And that looks like this. We're increasing, but as we keep increasing and increasing, we're increasing less and less fast. So that's the sort of graph shape here. What are the other permutations? Well, if f primed is negative, f double primed could still be positive, which would mean we are increasing. Decreasing, but concave up. So if you're decreasing and concave up, that looks like this. And then the last sort of possibility here is that you're decreasing and concave down. That would mean f double prime is negative. F prime is, I'm going to stay consistent here. F prime is negative and f double prime is negative. So we would be decreasing and concave down. That looks like this. Okay, so these are your four possible graph shapes according to the signs of the first and second derivatives. You can be more detailed than this, but really this is enough to get very, very good sketches. We want to get good at recognizing from the picture whether we're talking about concave up or concave down. And we also want to get good at finding algebraically where we are concave up and concave down. So stuff like this in general, this is all concave down. And stuff like this in general, this is all concave up. So here we are increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. And we split them into these four kind of groups. And you can glue anything that looks like this to anything else like this, right? You can glue a piece that looks like this to a piece that looks like this. You can glue a piece that looks like this to a piece that looks like this. You can glue a piece that looks like this to a piece that looks like this, and you get all sorts of things that look like these. If we return to the example we were looking at in Desmos here, you see that over here, everywhere over here, we are concave up, yeah? But then over here, we are concave down. So somewhere around here, we changed from being concave up to concave down. Now, everywhere here, I know we're going a little bit over time, just hang in there with me. Everywhere here, we're concave down, but everywhere over here, we're concave up. Nala, no. So somewhere around here, we had to change from being concave down to concave up. Those are those 2 points you saw me graphing at the very start. Minus what fuck me over here? F of this thing. This point right here is called an inflection point. And there's another one of them. I change these pluses, or these minuses to a plus. There's the other one. So you might ask, how do we find these? Right, you see everywhere to the left of this point, the graph is concave up. And then at this point, it changes and becomes concave down. And it stays concave down until you get to this point where it becomes concave up. The last thing I'm going to do for you today, and then I will let you go, is define an inflection point and tell you how to find them. They come together. The definition tells you how to find it. An inflection point is a point on the graph of f of x where the concavity changes. Concave up to concave down, or concave down to concave up. How would you find such a thing? Well, these will be places, suppose f of x is twice differentiable if f prime primed of x changes from positive to negative, or from negative to positive at x equals c, then the point on the graph of the original function c comma f of c is an inflection point. And this is just this theorem maybe isn't even worth calling a theorem because it's an immediate consequence of the definition. So somewhere you change from concave up to concave down, or concave down to concave up, is called an inflection point. Concave up means f double prime is positive. Concave down means f double prime is negative. So if you have a x value where f double prime goes from positive to negative, that means the original function goes from concave up to concave down. So that's an inflection point. Or if f double prime goes from negative to positive, that means the original function f goes from concave down to concave up. That's an inflection point. The kind of classic examples, and you've got this example here, and I hope that you guys can see this. Maybe consider taking a screenshot so you can look at this later. The other classic example is your sinusoids. They all have inflection points at their roots. So maybe I'll graph two periods of sine here. That's 4 pi, and this should be about 2 pi, and this should be about pi, and this should be about 3 pi, which means this is quarter period, quarter period, quarter period, quarter period. So you know what sine looks like. Oh, sorry, this isn't going to be up here, so it's going to be right there. Yeah. So like this. So this bad boy has inflection points at all of its x-intercepts, right? That's the idea here. So this is an IP, this is an IP, this is an IP. This is all concave down. This is all concave up. This is concave down, and this is concave up. And sort of our IPs chop things up. What is the second derivative of sine x?
Negative sine x.
Yeah, the second derivative of sine x is negative sine x. So notice we're concave down everywhere here. The second derivative would just be the negative of this. We're concave up everywhere here. The second derivative would just be so the sign of the second derivative corresponds to the concavity of the original. This is a fun example to look at when it comes to all of these things. And this is where I will leave it. So, you know, consider these guys and consider this example that we played with earlier. The calculation of these inflection points just comes from taking the second derivative of this function and playing the number line game with it. That's how we find the IPs. We'll talk more about this when we go through section 4.5 on curve sketching, but before we do that, we need to learn a little bit about indeterminate forms and L'Hopital's rule. And that is what we are going to learn. It looks like she might have already left. That's what we're going to learn on Friday with our next bit of student teaching. So please make sure you show up on time for Friday and get ready to learn about something pretty exciting. We're going to learn about L'Hopital's rule. And that is it. I will leave you guys here for today. The new homework is out. Please do work on that. Get as much of it done as you can. And we'll pick it up from here on Friday. Take care, guys. Also on Friday, be ready to vote. Be ready to vote for whether you want your exam before spring break or after spring break. It'll be up to you. Okay, that's it. Take care, guys.